Welcome everybody. So in the previous week we have been talking about interprocedural static analysis, and in particular I've talked about this challenge of unrealizable paths. So we saw that if you simply connect your intraprocedural control flow graphs together to an interprocedural control flow graph using the call graph, then you can basically get paths that cross procedure boundaries in, let's say, unexpected ways, because you basically call into a procedure but then return to a different procedure. That is something that we need to avoid if we want to make sure that the static analysis only simulates data flows along such paths that are actually realizable at runtime. If we were not to do that, then we could get false analysis information. In particular, usually you would get false positive information. So even if you have a context insensitive static analysis, it's typically still sound, but it's horribly imprecise because it inspects all these unrealizable paths. And so this week we will be talking about how to avoid this using so-called context-sensitive analysis, and in particular we will be talking about one approach that used to be very popular several years ago or decades ago, I would say, and it still sees, it still has some prevalence even today, and this is called the call strings approach. So today I will be talking about the general notion of context-sensitive analysis through so-called calling contexts. And also I will explain to you what context sensitivity means in general. But then we will also go a little bit beyond pure calling contexts, and I will also talk a little bit about object and field sensitive analysis that can be obtained through so-called value contexts. We'll still be talking about the latter quite a bit in the next few weeks, but already this week I want to give you a bit of information about this. So let's talk in general about how to conduct context-sensitive analysis. So analysis that basically address this problem of not wanting to analyze unrealizable paths. There are these ways that I just mentioned. In particular, there is the call strings approach, but there are also even more crude techniques that one couldn't think of, and that are also still appearing every now and then in the scientific literature. So the first possibility that you can think of is called cloning, and as you will see, that's actually really pretty crude. So let's assume we have a program such as this that actually has several calling contexts, right? So let's assume we want to do a constant propagation for this program here. Then you will see initially I is 0. Then we pass this to the inc method, which increments the value. So j ends up being 1, then we increment again, and k ends up being 2, okay? And now you will see that if you analyze this procedure here context insensitively, then you might get incorrect or unsound information because, for instance, a value that is computed here as a possible return value of this procedure will be returned not only back here but also back there, right? So the value 1 or 2 would both be propagated here and there, so that's obviously not a good idea. But what you can do now is you can basically distinguish these two different calling contexts, so this one here and that one here, by generating clones of that procedure. So what you basically do is you take your increment method, you rename that one to inc1, you create a second one, inc2, with identical contents, and then you simply also rename the appropriate names here at these different call sites. So now you have cloned this procedure into this one, and what you get is basically two independent calling contexts. And now this would indeed, for this program, give you a context-sensitive analysis, right? Because now the value 0 is propagated here, it's turned into 1, which is propagated there. which then goes here, it's incremented again, and it's returned to there. Here you end up with the return value 2. So you can do this, but you can see that also this is an approach that has quite some overhead, right? Because basically the only thing we needed to do is to make sure that we are returning to the right procedure. And this now can be done because for every procedure call, we are basically generating a clone of the callee method. So you can say the return edge is basically encoded in the identity of this clone. That's a possibility to do it that way, but it also comes with a very strong overhead. So it's quite inefficient. You require a new copy of a method for every single context. And realistic programs, they can have millions of such calling contexts. And in particular, you have to see that cloning is typically not enough or not sufficient to do it on a single level. So you might not just have to clone a single callee, but you might also have to clone its callees. So it's basically you have to expand a tree of possible callees, and that can quickly make this intractable. And also cloning method bodies is an expensive operation in its own right. You have to create new objects in memory, and it's, yeah, you can imagine it's quite some work that the analysis has to do. But then there are also some very foundational boundaries. So in particular, this whole approach, for probably obvious reasons, it cannot handle recursion. That's because, like I just said, it's not sufficient to just clone a single callee. You also have to clone its callees. And then if you have recursive calls, well, you would end up cloning forever, so you can't really do that. And then you have to bound this at some point. And then the question is, how again do you then deal with this, right? So basically you would then only clone up to a certain level, but then lose context sensitivity for anything that goes beyond that level. So it's a very simple and I would say crude model. It's also easy to understand. So I guess these are the advantages. But excuse me, beyond that, it's nothing that I would really recommend. A second possibility is inlining. Take a look at this program for a second. So what do we have here? Basically, we are starting with the same program here on the left-hand side that we had before, okay? But now instead of cloning the different procedures at these different call sites, we did a different trick. So basically, we took the procedure body that you see here, and we inlined it into these different call sites. So basically, you could say this call here is replaced by whatever is in this method body, and the same is true for the second call here. So what you need to do then is you need to rename these formal parameter accesses, like x here, for example, to the actual parameters here. So that's done here by actually such an explicit renaming, right? So I here is actually mapped to an x1. Then here we have the method body that we previously had. And then here, this is the assignment of the return value. So this y is being named to y1, which is then being assigned to j, okay? And then here you see sort of the second copy of this method body. When you do this all the way through your program, you basically end up with a single procedure modeling the entire behavior of this once potentially very large program. So that's a second possibility. So you insert the body of a callee at the call site into the caller. Like I said, the good thing about this is you end up with a single procedure, so you can actually afterwards do a simple intra-procedural analysis, and we have all learned how this works, right? So you can just use your good old MFP-based analysis using the monotone framework, for instance. But there are also some disadvantages of this. So the bad thing is, for instance, also that procedure abstraction is completely lost. So you don't know anything anymore about where procedures originally were. That means the analysis also cannot exploit procedure abstractions. And as we will see later, it can actually be quite advantageous if you do exploit such abstractions. So later on, we will see other types of analysis, for instance, that summarize the effects of procedure calls. And obviously, if you don't have procedure calls anymore at all, then there's nothing you could summarize and work with. So that's actually a problem. But then there are also, again, more foundational limitations. So also here, you have an exponential blow up, which makes it very inefficient, right? So again, it's not sufficient to simply inline callees on the first level. You actually have to inline them across several levels. And then that can make your code base blow up quite a bit because basically you can have an exponential number of procedures to inline or copies of procedures to inline. And that's similar to cloning. That also won't work for recursive programs, right? Because of the same limitations. I would say if you want to do this for real-world programs, it basically can't really work, right? And also these days, I have to say, when I still see programs when I still see papers where people implemented context sensitivity with cloning or inlining, to me, that's really a bad smell because it typically shows that people didn't really know any better, right? So they didn't really know what they were doing. And I would say these techniques both should actually not be used anymore these days. We actually have both more precise and more efficient techniques that are always preferable. But just to provide you some context. So these are approaches that certainly have been used quite a bit in the past and that you will also find it quite a bit still in the scientific literature. But let's talk a bit more about how it is actually done in practice. And when you talk about this, then there are basically two different approaches that come to mind. And there's the so-called call strings approach and the functional approach. And the call strings approach and some flavors of it we will still be talking about quite a bit this week. And the functional approach we will be covering in the following weeks. It also comes in a number of different variants. So we will be looking at the functional approach a bit more deeply even, actually. But first, let me contrast the two different approaches because fundamentally they actually are very different in spirit, although at some point we will also see that there's actually a way to unify both of them to some extent. So in the call strings approach, the main idea is that we want to extend data flow facts with explicit context strings. We'll be seeing context strings in a minute. Basically, they are explicit representation of call frames. So they encode information of what methods are basically currently on the call stack. And therefore, they tell for any given data flow fact where the data flow fact originates from which procedures does it come and where does it need to be returned to, therefore. Then callees, because of that representation, are actually re-evaluated for every such extended data flow value. So if you have different data flow values with different calling context strings, they are evaluated independently. That gives you context sensitivity, but it also has some drawbacks, like we will see later. What's also nice about the call strings approach is that it's universally applicable. So that means any analysis that fits the monotone framework can be almost trivially extended to be an analysis in this call strings approach. So that's what I mean by universal applicability. But there are some problems with recursion that I will get back to also in a few minutes. Then there is the functional approach on the other side. So there, the idea is quite different. So in the functional approach, we want to compute for each callee, so each procedure that is called in the program, a summary function. And that's why it's called the functional approach. So every procedure that I call is represented by a summary function. And the idea is then that this function represents the behavior of that callee independent of any possible input value. And once you have that function, the nice thing is then that this function can then be applied to every relevant calling context. And because this function is independent of input values, you can apply to different input values and you will obtain different results. And that makes the approach context sensitive. What's nice about this approach is that it can actually deal with recursion, and it can even give you, in most instances, full precision, even for recursive programs. But summaries, unfortunately, are not always possible. So there are some restrictions that we will be talking about, and you need to have these restrictions, otherwise the functional approach cannot really work. So there are certainly program analysis that you can address in the call strings approach, you can implement them in the call strings approach, but you can't really do that in the functional approach, unfortunately. So let's talk about this ominous call strings approach in a bit more detail. So what does it really look like? Like I told you, we desire to encode the call stack and individual call frames somehow within data flow values. So if you assume that we are given a regular context insensitive data flow analysis, then this will propagate data flow values D throughout the interprocedural control flow graph, right? And now the idea is that we augment this fact D with additional information, namely each such fact D will get its own call string, and the call string looks like this. So it's basically a concatenation of individual call frames, and the call frame is simply represented by a call site. So C0, C1, CK, and so on. So these are call sites. So you know, if you were to implement this in Suit, this could be a statement. It could also be an expression, an invoke expression that actually does the call. That's not so relevant, but basically you need to have some representation of a call site. And these form a stack. So, you know, for instance, C0 could be the main method of the program, so it would be your initial frame, and then you have here some procedure that is called out of main, and then this is calling another procedure, and so on. So your stack grows into that direction here, for instance. And now, if you need to return a fact into the caller procedure, then because this fact D now has been extended to such a tuple that comprises not just the fact itself, but also this call stack, when you return that fact to its caller, you can simply look at the stack and you can see, oh, my top stack frame here is actually CK, and therefore I know that my immediate caller was actually this call site CK. And so you will return this data flow fact to just after CK, right? So to the statement that follows the procedure call within the original caller. And any program point P is reached by call strings that represent all possible sequences of unfinished calls reaching that point, right? So this is now a view of any single statement in the program. Such a statement is a program point P. And this can be reached by a number of different facts, and these facts all have these calling context strings associated. And all the call strings that reach this particular program point are call strings for possible sequences of unfinished calls reaching that point. They're unfinished because, well, of what I will be telling you in a minute. So basically, when you exit a certain procedure and you return such a data flow fact to its caller, then you will pop off the current call frame here, the top call frame of the stack. So basically shrinking the stack again, and therefore all the frames, all the stacks that reach a possible program point are just the one that are about unfinished calls that have not yet been popped off, so to say. C0 is always the starting point of the main method. And frequently this will also be omitted in actual representations because you can, it's always the same. So you can model that implicitly. That doesn't really matter. Let's take a look at an external example program. So what do we see here? So we have a secret value here that's passed to an identity method. Okay, so afterwards S here still will be tainted. And then we have a not secret value that the taint analysis would not be tracking, but that's also passed to the identity method. And the identity method is represented here, so it's simply just returning its parameter value. And here we see now an interprocedural call graph representation, control flow graph representation of that same program. And you can see here now that I've labeled these edges with different colors. Because I know what it's supposed to be like, but in a context insensitive analysis, we don't basically have any colors, right? So the problem is then as follows. So if you taint this value S here, it's basically tainting P on this level here, so the parameter value, and it's then tainting R down here, right? And now the question is, given this taint value R, where does it need to be returned to? And because normally we don't know anything about these return edges, we just know that R is tainted and it should be returned to potential callers. In a context insensitive analysis, we would now return here to taint S on this level and to taint V on this level. But that down here would actually be a false positive, right? Because assuming that not secret is actually an untainted value, V should not become tainted here, right? And the taint is falsely identified here because basically this taint is going into ID and it's exiting here, which is unrealizable, right? It doesn't really make any sense. So let's take a look at how the call strings approach improves over this. So in the call strings approach, first of all, we would label these two call sites here, with some identifier, C1 and C2. Like I said, you can use the actual statement as a label. You can also use this call expression here as a label. It doesn't really matter. What matters is only that these labels, they basically uniquely identify this particular call site. Then here we have an initial data flow fact which is labeled with S main, like I told you before, and with S, so that is representing that in the context of this main method here, S is tainted at this program point. And now we go into this procedure call, and this now means that this calling context string is extended, right? So previously we had this stack, and now we push C1 onto the stack, which you see here. And we still transfer the taint from S on this side here, so from the actual parameter to the formal parameter P on this side. Now, then this taint is simply being propagated forward. So here we have now still the same stack. So within a procedure, the stack actually never changes, so that is not updated. But we're still carrying forward the taint from P to R, simply like we would have done in a context-insensitive analysis. And now the nice thing is that because of this additional information, we know how to return this data flow fact only to the right caller, right? Because now we can look at the stack, we can identify that C1 is actually the relevant stack frame here, and therefore this should only be returned to this calling context here, so we will be returning S main S to just after this call site, and only there. So we will not be returning anything at all to this program point. Also note that from here to there, this stack frame is popped again, right? That's what I told you earlier. So when you basically process a call edge, then you're pushing a stack frame onto the stack, and when you're processing a return edge, then you're popping that stack frame off the stack again. And therefore, at any program point, for instance, at this point, all the facts that you get here are all the effects of unfinished procedure calls that have reached this program point, right? So this, for instance, here was an unfinished procedure call that originated here, and it led you to this program statement. And like I said, typically you can also often omit as main. It's usually not important. You can encode that implicitly, and we will typically also not encode that explicitly in the remainder of these slides. So the general algorithm, it looks as follows, and I think you will agree that it's actually really simple. So call edges, they push a call site on the calling context stack of each propagated value, and a return edge returns only to the method on the top of the stack, popping the top element. And the rest is really totally identical to a flow insensitive analysis. So it's really a very natural extension, you could say, of the monotone framework. Has not a lot of magic. There's only one other thing that needs to be taken care of and needs to be kept in mind. And that is that you need to specially treat merge operations at control flow merge points. Remember that in the context insensitive analysis, we had a very simple domain, right? So we were basically propagating our regular data flow facts, but now here we have basically extended our abstract domain, right? We have extended it with these calling context strings. And that also means that we need to extend the merge operator to these extended data flow facts. We somehow need to tell the analysis, what does it mean to merge calling context strings, and when is that actually correct to do? When do we want to merge them and when not? And in order to understand this, let's take a look at the following equation. So here, L, which you will find at these 2 points, is actually the lattice or the abstract domain, okay? And now let's assume we are actually merging, so that's our special merge operator here, 2 of these extended data flow facts, X and Y, okay? And they have this shape, so they're basically pairs, and they have a calling context string on the left-hand side. And then they also have some data flow values on the right-hand side. And so this capital X in particular looks like this, right? So you have, in the first case, you have some sigma here with X, and then also you have some sigma here with Y. And now what you will see here is that these two calling contexts, they are identical. That's what we assume in this particular case, okay? And when they are identical, then it means that here we have 2 data flow facts that really relate to the same contexts. And these are also data flow facts, therefore, that relate to the same realizable paths to your program. And then they should be merged. They should be normally merged according to your regular merge operator, right? And that's exactly what we do. So we merge them using whatever merge operator you would have chosen also in your context insensitive analysis. So this now operates only on the bare data flow values. And you create a new fact that associates that resulting fact here with the same calling context string that we had here earlier. And it's one and the same because this was identical on both sides to begin with, okay? Then also we do the following. So if you have a data flow fact that is contained here in X, okay? And then for all other data flow facts that are part of the lattice, which are not contained in Y for the same particular calling context string, we only retain this particular X, okay? So this is basically saying, okay, if there's no other data flow fact that relates to X for the same context, then simply retain X as it is, because basically, X stands on its own, and it has no relationship to the other data flow facts, because the other data flow facts, they only relate to other calling contexts, and they don't matter to us right now. And therefore, X is retained, and the rest we don't care about, okay? Inversely, then, we also do the same for the other side. And that basically concludes the merge operation. So what this really means is we merge facts only if their context is the same, right? So this is happening up here. And all the other data flow facts that relate to different calling contexts, they are retained, but they are not merged, okay? So merging is happening on identical contexts, but not on different contexts. I know this equation might be a little hard to digest, so if you're still unclear about this, maybe go through this with a couple of examples in your own time. Now, this might look nice and simple, but it's actually too good to be true, because there are still some problems with the calling context approach, in particular when it comes to recursion or also otherwise large programs. And that I will be talking about after a brief break, so I'll join you back in the next video. Thank you so far.